Okay, so here we're going to be looking at a very specific type of integral, and it's called the p integral. It's really going to be of this format. So we have integrals 1 over x to the power of p, and we are integrating from 1 to infinity. Now, if you remember, the first two examples that we did with improper integral, we looked at this one, the integral of 1 over x squared from 1 to infinity, and we said that this one was actually equal to 1. It was convergent. And then right afterwards, we did this one, 1 over x from 1 to infinity. And this one, we said that actually the limit went to positive infinity. It was a limit that did not exist. And so that integral was divergent. And after doing these two examples, we talked very briefly looking at what it meant for these functions to go to 0 fast enough. And I had mentioned, the indeterminate form 0 times infinity, because even though here the interval is going to be infinite, meaning the base width was going to be infinite, we said that each of these functions themselves was approaching 0. And there was a struggle between the two of them, the 0 and the infinite, and we said we are interested in knowing what it means for a function to go to 0 fast enough. So let's take a look. And so here we have our two functions again. We have the red one, 1 over x squared, and we have the black one, 1 over x. And we looked at the area underneath the two of them. So here we have the area underneath 1 over x squared. That was the area that was equal to 1 ultimately, and it was convergent. But we have the area underneath 1 over x, this black area, which we said was too large. That function did not go to 0 fast enough. That area was divergent. Now, when you look at the two of them, yes, there's definitely a difference in terms of how quickly they individually go to 0. One of them goes to 0 fast enough. That's 1 over x squared. One of them does not. Okay, so what we're going to look at here is what happens if we look at just a generic p integral. So what if we look at the function 1 over x to the power of p, which we've set up here, and you'll notice we have a slider here. We can adjust the values of p to see how our function actually behaves. And we're interested in this area underneath this curve from 1 to infinity. We want to know when is this going to be a convergent area, when is it going to be divergent. So let's sort of play around with the values of p, get an idea for what they do. So the first thing you'll notice is that if p goes from being positive to negative, our function changes from decreasing for positive values of p to increasing for negative values of p. And if we have a negative value of p and our function is increasing, this area here is certainly going to be infinite. Okay, if you have an increasing function, there's no way for that area to be convergent. So that's the first thing. The second thing is when we go over to positive values of p, yes, our function is now decreasing, but for a small value of p, something like 0.2, our function is not decreasing very quickly. That area is still very likely to be infinite and to be divergent, but we definitely notice that as we increase here the values of p, the function begins to decrease faster and faster. It approaches 0 faster and faster, and so for large values of p, this region is very likely to be convergent. It's very likely that the area is going to be a finite area. Okay, so very much what we're interested in this section is what is the difference here? What is going to be that perfect value of p in between the integrals that diverge and the integrals that converge? And so we have a little bit of math to do. So coming back to this, we're looking at our p integrals. We want to know what values of p those integrals are going to be convergent for and which one they're going to be divergent for. So here we have our question, for what values of p is this integral going to be convergent? So we have to actually set up this improper integral and evaluate it. Right away, it's type 1. Okay, we have t approaching infinity. We introduce our parameter. We do the integral from 1 to t. Now we want to find our antiderivative, which is not going to be too bad because really our function here is just x to the negative p. We can use power rule. We increase the exponent by 1. We divide by the new exponent. So that seems okay. When we go and plug it in, we have limit of x to the negative p plus 1 because we increased that exponent, and we divide by the new exponent, and we would evaluate this from 1 to t. Now, the one thing that you may have already noticed is that here this works fine, except that what if p is equal to positive 1? If p is equal to positive 1, there's one major issue, and it's right here in the denominator. We have division by 0, so that's going to be a problem. And actually, even sort of taking that one step back, looking at the integral, if p is equal to 1, then we're actually doing the integral of 1 over x, and the antiderivative would be ln of absolute value of x. It would not be using the power rule like we just did. So we have to sort of fix this a little bit, and this is going to make the question a little bit longer. Okay, we're going to have to split it up into different cases, and those cases are very much going to depend on what value we're considering for p. So the first thing is that everything we do from here on, we are going to be assuming that p is not equal to 1, and then at the very end we can come back and consider the scenario, what happens if p is equal to 1. So fine, if p is not equal to 1, then this is how our antiderivative is going to work. And now let's do FTC2. We still have limit as t approaches infinity, and let's sort of rearrange this a little bit. I could take out this constant, okay, and let's just rewrite it a little bit. It's actually just going to be 1 minus p, and then inside I'm going to do FTC2, okay, and we're going to be replacing x by t. So we would have here t to the negative p plus 1. And then we're going to subtract what we get when I plug in 1 for x. So that's going to be 1 to the power of negative p plus 1, except that we know here if p is not equal to 1, then this is a non-zero exponent, and actually we get that this term here is just going to be 1. So let's rewrite this. We still have our constant 1 over 1 minus p, and here we have t to the power of 1 minus p, and we have minus 1. So now we would like to know what is going to be the value of this limit, what happens here as t approaches positive infinity. Okay, and this is where we're further going to have to divide it into cases.